Okay, good morning everyone. You already now know the style that I'm going to adopt and the way in which I present material. This is a continuation of the story that I began yesterday. This is all part and parcel of trying to give some very general, I hope relevant and interesting background to the water wave problem, being my particular version of the presentation of the material. You're seeing a different, more formal and rigorous presentation from Catherine. My intention is to try and give I suppose I would call it the applied mathematical slant. The continuing story is in part covered by those two topics that I want to look at during the first part of today's lecture. As I said yesterday, the same will apply today. I really don't know how long exactly this is going to last. I've never actually given this precise lecture before. I just sat down and thought about what needed to be covered, and there will be a break before we move on to the second part. So, just in a few words, I'll be a little bit more precise about what we're going to try and do this morning. I'm going to look at two absolutely classical standard problems in water wave theory. The first one, the one that I'm sure we've all heard of, the solitary wave, as a property of wave propagation in the water wave context, it plays a quite significant role. Much more importantly, of course, it is the starting point for solitary waves, solitons, inverse scattering theory, and everything else. So in that sense, it holds a very important place in the whole panoply of nonlinear wave propagation. Gerstner's exact solution is perhaps something that you won't have come across. It is the only non-trivial exact solution. It's got some very peculiar properties, and in consequence, it's I may say this again later on, a mathematical curiosity, but of no great practical importance. At least that seems to be the current view. So, let's get and in the second part, I should just mention, I'm going to give you a very brief introduction, an overview of parameter asymptotics. Again, I don't know your backgrounds. The chances are quite high that the sort of approach, the very formal approach that I use is not something you're that familiar with. So I want to just introduce you to it and the language and just the underlying ideas in a very simple-minded way, so that when I use the techniques later on this week to look at more complicated fluid mechanical flows, you'll have some idea of the way I'm thinking about it and maybe where it's relevant, the language that I use. Okay, so we start with the solitary wave, and I suppose I really need to start with this gentleman, John Scott Russell. There's I'm going to chatter now for a few minutes. By the way, that's one of the downsides. I'm not precisely sure what I'm going to say to you. I've got some ideas here, and what I say tends to be, the phrase I would use is, as the spirit moves me. So I cannot be sure exactly how much detail I'm going to go into here, or more particularly, how long it's going to take. Right, well, John Scott Russell, he was born in 1808. He was a Scotsman, and he became an eminent scientist and engineer. In the few years before that date, 1834, maybe 3 or 4 years before that, he was still very young, as you will see, he was appointed by the company that owned the Edinburgh-Glasgow Canal to design the shape of barges that were pulled. Now, we're going back a long time. This is when we used to carry things around, coal, etc., in barges, in our canal system in the UK, pulled by horses, of course, hence did you realise this? The tow path at the side is for the horse towing the barge. So it'd usually be one horse on one side, not a pair of them, just one, and then there would be, and the boat would only just fit through the canal with some rudder control, and essentially they were pulled by a horse. They were towed along. However, the various companies were very concerned, not unreasonably, to travel as fast as they could, bearing in mind you're being pulled by a horse. So they wanted to reduce the drag as much as they could on the barges. And that's where John Scott Russell came in. So he was charged with trying to redesign the hull shape of the barges to minimize. Are you still happy with it? You're happy for me to carry on talking? Yeah, okay. There's no mathematics here. And he started to do some experiments. Now, the experiments were literally full scale. So he would make some adjustments to the shape by adding a bit of wood or taking off a bit of wood, getting a horse to pull the thing along and carry out some measurements. And while he was doing this, he made an intriguing observation. The observation was actually made, the crucial one was in 1834. And he produced the results in a paper which came out in 1844. And it was, for them, a conventional research paper. It is so unconventional for us that I'm going to have to read a little bit to you. So, this was presented, it was called the Report on Waves. It was presented in 1844 at a meeting of what was called the British Association. Nowadays, it's drifted into the British Association for the Advancement of Science, I think. In those days, 1844, there was really no scientific meetings of the sort that we're familiar with, very specialist, in very specific areas. And it was the forum in which the results were presented. I should add one other comment before I move on. That has drifted, changed very much, so that by the time we get to the end of the Second World War, it really became a public forum where anybody with any scientific interest, and it would move around cities in the UK, would turn up and present in very general outline their scientific results, their interests to the public. Okay, it became a public forum. And I can remember when I was rather younger than I am now, there would be reports in the newspapers, in the quality newspapers. There would be reports of the various topics that were discussed the previous day at the meetings. Nowadays, it's hardly reported at all. Sad reflection on the way we're going. However, so I'm building up to it. I'm nearly there. I will have to read this with a little care because the language is a little unusual. Okay, so this is what John Scott Russell wrote about what happened to him during one of his experiments in 1834. I believe I shall best introduce the phenomenon by describing the circumstances of my own first acquaintance with it. Let me pause there straight away. This is a bona fide scientific paper. I wonder how many of you would be writing using that sort of language. And it gets better or worse, depending on your point of view. I was observing the motion of a boat which was rapidly drawn along a narrow channel by a pair, in this case it was a pair of horses, when the boat suddenly stopped. Not so the mass of water in the channel, which it had put into motion. It accumulated around the prow of the vessel in a state of violent agitation, and then suddenly, leaving it behind, rolled forward with a great velocity, assuming the form of a large, solitary elevation, a rounded, smooth, and well-defined, heap of water, which continued its course along the channel, apparently without change of form or diminution of speed. I'm going to pause there just for a minute. There's only a couple of sentences to go. Now, that is the style, more or less, that many research papers are written in. Okay, there will be rather less flowery language and a little bit more mathematics, but it was very open and chatty. You really thought about what you were going to say. Diminution of speed. I followed it on horseback. How many of you do your research and follow it up by following it on horseback? So I followed it on horseback and overtook... even though I've read this hundreds of times now, I overtook it, still rolling on at a rate of some 8 or 9 miles an hour, preserving its original figure, some 30 feet long, a foot to a foot and a half in height. Sorry, a foot and a half is about half a metre. So are you comfortable with feet and metres? It's a bit old-fashioned. Preserving its, from a foot to a foot and a half in height. Its height gradually diminished, and after a chase of 1 or 2 miles, I lost it in the windings of the channel. Now, that was Scott Russell's first meeting with this wonderful wave. And he was so intrigued that he went back home in Glasgow and started to do some experiments. That's why there is a gap in a sense, because he first observed this in 34, and he then went back home and over the next few years did lots of experiments. Very simple experiments. He built a channel about 6-7 meters long, filled it with water, okay, put a large block and dropped the block. Different distances, and lowered it, sometimes fast, sometimes slow, just therefore causing a wave to be generated. As it went down, the wave would be generated, and off it goes. And he did an awful lot of experiments, able to form very simple, pure, single solitary waves. He measured the speed, and he measured the height, and he was able to say, for example, that the higher waves travel faster. What he also found, where's the board rubber? Can you see the board rubber? Oh, I can see it now, yes. I don't think many people have observed this. I've got a copy of this paper, and he draws a large number of curves based on his experiments. Remember, he couldn't photograph it. He couldn't record it in any accurate way. He literally had to look at it, measure the height, and sort of think, well, okay, the shape's a bit like this. And of course, he couldn't do anything else, and he drew it. He produced a lot of curves, but one of them is rather intriguing. He found that if he generated this wave in just the right way, he got a wave that looked like a conventional solitary wave, but it propagated and became, you'll actually find in that paper the two-soliton, well, we call it now, the two-soliton solution. Obviously, he didn't know what he was looking at, and he didn't make any comments about the fact that the one had broken into two. But his pictures are absolutely clear, that you've got locally two solitary waves, and the larger one, traveling faster, is at the front. Right, so that's, I need to, yes, sure. No, that's a good question. There is no evidence that he tried to make them collide. Many years ago, when I give talks to students, sometimes in schools, I would have a long channel, and I would make them collide. In other words, I'd start one at one end, run at the other end, start the other one, and watch them go. Yes. No, he didn't. He was literally just firing them off, and I'm not sure how much care he took about the end here. I'm assuming, and I really can't remember, he should have put in a little shingle beach or something here, so that he didn't have the reflections, but he wasn't worried about that. He was literally starting, following, and that was the end of the story so far as he was concerned. So no, there's no evidence that he collided them, but he certainly, without realizing what he'd done, had produced what we would recognize as a two-soliton solution. Thank you. Right, yes, I was going to say, just finish off with John Scott Russell before I go back to what was thought about in terms of theory at the time. John Scott Russell got much involved with Isambard Kingdom Brunel, and Brunel used him to design the hull shape of his Great Eastern, one of his wonderful big ships. I'm not going to tell you any more about the big ship. If you're interested, go and read about it. It was eventually launched in 1858. I say eventually launched, well, perhaps saying eventually and giving you a date is a little misleading. It was launched in 1858. Unfortunately, it took approximately 3 days to launch it. Brunel had invented, he thought, a super special, easy way to launch the boat. It didn't. It took Brunel 3 days to work out the way in which to get this ship into the water. That is clearly another intriguing story, but not one I'm going to tell you here. I'm just trying to check. Well, one more thing, yes, about him. He was also one of the founding members of the Institute of Naval Architects in the UK. So he really was the father of naval architecture in the sense of designing hull shapes, that sort of thing. Okay, well, let's turn back to what was thought at the time. Now, we're talking about 1830s, 1840s, something like that, or 1840s, 1850s. And the one person you would go to in the UK at that time was Airy. Airy was the preeminent applied mathematician. He knew a lot and he did a lot. So they went to Airy, a number of the scientists, mathematicians, whatever, went to Airy and said, well, this wonderful wave, look at it, look at all these pictures, please, can you explain it to us? Sorry. Are you still happy for me to carry on? Airy said, it's impossible. It cannot be done. No, there's something horribly badly wrong here. Even though I assume they would say to him, look out of your window. Look, there it is. You're seeing it. This is basic physics. How? And that actually was the case for a number of years until 1871 Boussinesq and 1876 independently Rayleigh realized that you need the right balance of terms. You need the dispersion and the nonlinearity. And that was something which, for whatever reason, Airy wasn't able to pick up on. So they were able to confirm that a reasonable balance was possible within the equations. They got the Scheck squared. I prefer the Scheck squared Scheck pronunciation. Some of you were going to say Sech, I suspect. I was taught to put the H early on, if ever you could, in the word. So SECH squared profile. And of course, it confirmed that the higher waves travel faster. All right, so I think that has brought us up to date in a sense. And of course, after that, although it's not directly relevant to what I'm going to say now, we've got Korteweg and de Vries, and I'll say a little bit more about them in 1895, and so the story goes on. Oh, by the way, Scott Russell called this thing the Great Wave of Translation. Beautiful title. Okay, so let's get started. We're going to look at the simplest possible scenario. So, irrotational, one-dimensional traveling waves moving at a constant speed with a fixed shape. So we're looking for a solution of that form. Water of finite depth and stationary conditions at infinity. Introduce a velocity potential and use the pressure equation, or unsteady Bernoulli if you want to call it that, to get the appropriate boundary condition at the surface. It's the one that I mentioned yesterday, and it's at this point, if you need it or you're interested, the very simple little derivation that gives you that is on page 10 in the notes. Okay, so the non-dimensional problem will then look like that. At the moment, I'm retaining the notation that I had yesterday. And as I will say in a moment, I realise that isn't quite how I should have written it, as you'll see in a moment when I uncover this. Okay. We're considering arbitrary amplitude, so we're not specifying that it be necessarily a small amplitude, so we can just set epsilon equal to 1. Now, this is where I need to just make the obvious adjustment. Bearing in mind what I said about scaling out the delta, this should have been written with the definition of the variables via the scaled variables that replaces delta squared by epsilon everywhere, and then you put epsilon is equal to 1. So don't be misled by the presence of the delta squared. It doesn't play a role, and it would look neater if I had removed them from that particular set of equations. So those are the governing equations. Seeking a solution of the type that I mentioned a couple of minutes ago, we're looking for a solution of that system. An approximate solution of that system was what Boussinesq and Rayleigh had found, and approximate in a different sense gave us the Korteweg-de Vries equation. Okay, so what I'm going to try and do here, there are quite a number of general properties known about this particular flow. So what I've described here in schematic form are the various properties that can be proved for the general solitary wave. So what we've got here, here's the wave, and it is moving. It's not in the moving frame, it is moving here. So we've got zero conditions ahead and behind. This is a normalized, or if you like, a non-dimensionalized system. So the undisturbed free surface as at z is equal to 1. There is the surface wave, the solitary wave, propagating at a speed c. We have got w is equal to 0 on the bottom, By symmetry, we have W is equal to naught there, W tends to naught there, but because, of course, the kinematic condition, we find that W has got to be positive here to satisfy the kinematic condition on the top there, and negative over here. We are, of course, solving Laplace's equation for the fluid. Below the crest, then there is an induced motion. It gives you a U in this direction, which is positive, as I've already indicated, 0 at either end. Now, those various statements there are things that we can prove about the general solitary wave. We do not have an expression for the general solitary wave. A lot of work has been done, I guess probably started by Longet-Higgins in the 1970s to get very, very good numerical estimates for the surface wave, the shape of it, and its various properties. Okay. Yes, for irrotational flow, then the existence of a steady solitary wave has been proved, but as I've already said, there is no closed form solution. There is another special result which I'll refer to, and I'll be able to give you the name of that. I can't remember. There are, in fact, many names here are associated with the existence of the steady solitary wave. Okay. I've just mentioned Longet-Higgins. Now, Longet-Higgins did get involved via his analysis of some of the properties of the solitary wave to then move on to numerical work. And what he in particular did was to use and develop some new integral properties, integral relations for the solitary wave. He used this as a guide and as a check when he was doing the numerical work. So what I'm going to do here is just list the standard properties that are known and defined for the solitary wave. Some of these are absolutely natural and obvious. So we have a total mass. I mentioned that as part of the conservation conditions that we had yesterday. We can define the total momentum. And notice we are integrating this. We've got undisturbed conditions at plus and minus infinity, and psi, as I've indicated there, is of course the local characteristic variable moving with the wave, so x minus ct. So we are integrating from the bottom to the top. Z is naught, is the bottom. 1 is the undisturbed level. 1 plus eta is the wave. And from minus infinity to infinity. Right, so total momentum. We can correspondingly, and again, I have left the delta squared in here, but just ignore it. Set it equal to 1. Total kinetic energy of the motion. There's the potential energy of the motion. That was mentioned yesterday, I believe, as well. And the circulation. This is the integral being taken along any streamline. Once you've got these definitions, the issue becomes, can we deduce any relations between them? Rather simple and routine relations, and I'm just going to do a very simple one for you. In fact, by far the simplest. What I will refer to it more carefully in a moment or two, but I've produced a second rather more extensive calculation in the notes. Right, so let's just start with the equation of mass conservation. I have, because we're in a moving frame, using psi, I have shifted u by c. So now I've got d by d psi, not on u, but u minus c. And integrate, as we did yesterday, from the bottom to the top. Okay. If we then evaluate, sorry. Oh, sorry, that's the vertical velocity component. Yes, I've separated the horizontal from the vertical, okay? Yeah. So that's just the ordinary mass conservation in 2 dimensions. 1 horizontal, 1 vertical. Right, so we've got the result that we had yesterday. The integral from the bottom to the top, u minus c, is a constant. And if we evaluate that at undisturbed conditions, then we obtain that the integral eta tends to 0, u tends to 0. We've got this integral left, which must therefore be minus c in this normalized system. Okay. We then take the integral of u, which of course is related to the velocity potential, and yes, that's right, which will then be equal to c eta. Integrate that from the one end to the other of the domain, so from infinity to minus infinity to infinity, and we produce that. Okay, and finally, you can immediately interpret that. This gives us I, this is M, C there. This is one of the simplest, but not the first, elementary identity relating those integral properties. This was, as you see, found by a star in 1947. A much more sophisticated one is the one that I've outlined for you. The calculation here is far lengthier in the notes. So in this one, I'm going to draw a picture, which is just reproducing, and I'll make one or two observations about it, reproducing what is in the notes. This one goes back to, I think, 1897, I seem to remember, something like that. 1891. No, here's the bed. Here's the surface. We apply Green's theorem to a region which is bounded by a line there. I'll say more about this in a moment. There, the bottom, and the free surface. So we apply Green's theorem in that region where this is a finite point, as we set it up initially. I'm calling it minus psi naught and psi naught. You can apply Green's theorem, and then with care, I hope I've explained it sufficiently here, you do the obvious. You then can allow psi naught, to go to infinity. I'm doing all the evaluations around the boundary. All the details are spelt out towards the, I guess the details are towards the bottom of page 11, resulting in the result 2t is c into I minus c. That's on page 12, and I've quoted, I haven't done any derivations here at all, but go back to Longett-Higgins' 1974 paper. There's a further one, a 3v is c squared minus 1 times m. We have a number of these properties. These, as I've mentioned already, were used by Longett-Higgins as the basis for driving and checking the various numerical results that he developed with a number of his students. We do not have a closed form representation of the solution. I've said that already. There is a wave of greatest height, usually called Stokes's wave. It looks, there's a schematic of it, it looks like that. It was, I'm trying to remember the date, 1880. Stokes in, yes, sure.
How much of these identities extend to the periodic waves?
There are, I think, there are corresponding integrals for the strictly periodic wave, yes. But I don't know them off the top of my head, but yes, they do exist, there are some. Yeah. What was I going to say? Yep. Stokes, in 1880, analysed what was happening near the peak and produced, well, he used, I guess, complex variables. So we've got a two-dimensional, incompressible, irrotational flow. So we have a velocity potential and a stream function, and they satisfy the Cauchy-Riemann relations. So we can work, as you're very familiar with, in the complex plane, W being a differentiable function of the single complex variable x plus iy. What he then did was to look in the locality of the peak here and ask what happened, whether he could, and then what happened as you approached C. He was able to do the analysis locally and show that there was an included angle of 120 degrees here. So it was 120 degrees, and in passing, estimated, but very roughly, what the height of that highest wave was. This is 1, so the 0.83 is that bit there. What I think is comforting is that in, I'm checking the date, 1978, John Tolland proved the existence of the highest wave. So what we've got then is in, standing back a little, I've just given you an overview of some of the properties, and how it started in the first place, of the solitary wave. So far as we're going to be concerned here, for this story I'm trying to tell, it isn't really the solitary wave. It is the simplified version of that, the small amplitude version of that, that we're going to be interested in eventually. But bear in mind, in the background is a lot more information and a lot more is known about these waves. Okay, so I've already said this already. I can't be written in closed form. Oh yes, but quite a lot of asymptotic properties locally at the top, not necessarily the highest wave, and of course in the tails. Very easily done. Okay. For us, the more interesting aspect is the fact that we do have small amplitude approximation, small amplitude long wave, necessarily long wave. And then we produce, and I'm going to write it using my original variables. You'll see in a moment. There we are. There is the very famous small amplitude solitary wave. Now, I've written this because I've based that on precisely the equations that I wrote earlier, which have got the epsilons and the deltas in. If you carry out that transformation that I showed you yesterday, it gets rid of delta in preference to epsilon. That just takes this out altogether. This vanishes when you redefine x and t appropriately. So again, ignore those. You just get square root 3a over 2. The of size, you really need to retain it. You need to be reminded that we're dealing with a small amplitude wave, so I'd like to keep the epsilon in, but clearly it doesn't really play a role here. We see that larger waves travel faster. Not only that, by virtue of this factor here, the larger waves, higher waves, are narrower. Okay? So larger waves travel faster and are narrower. Oh, it's just the amplitude. Well, it's the normalized amplitude. Yes? Yes, well, sorry, it's the because of the numbers in here, I've chosen to replace a by 2a. I think that's maybe why you're asking about the 2. Ignore the epsilon, and 2a is the amplitude. Okay? Sorry, delta? No, the epsilon here, yes? Sorry, is eta. That's the symbol that I use for the free surface relative to the undisturbed state. I wrote 1 plus this free surface normalized 1 plus epsilon eta. Okay? Yes. Yes. So I've the formalism here then just gives us the solitary wave written in its conventional form. As I've said already, you can ignore the epsilons on the deltas. They don't really play a role here. Okay, oh well, here we are. This we've already know, and I'll say a little bit about the role it plays in soliton theory and KdV theory tomorrow, in the first lecture tomorrow. Okay, I've said this already, haven't I? So yeah. Okay, so I'm going to pause there for a moment, just see if there are any questions that crop up. So bear in mind what I'm trying to do. All of this is still background material. I'm trying to lay the foundations, much as I would if I was just introducing a very general course giving properties of the water wave problem and some of its solutions and what we know about them. This is very different. The Gerstner solution is something which for many years, well, I just ignored, I have to admit. I didn't think it was of any interest whatsoever. And it is, as I said a few minutes ago, regarded as a mathematical curiosity. It is mathematically very interesting. Maybe curious isn't quite the right word, but it is certainly debatable as to whether it plays any role whatsoever in meaningful calculations. However, the colleague I've worked with for many years, Adrian Constantin, did a bit of work on it and found, in conjunction with other work done by Molo Christiansen, which goes back many years, I'll say more about that when we reach the edge wave situation, he found that it was relevant to an important description of waves which are known as edge waves. It does play a role. It isn't quite the role that I would expect it to play, and that's one of the reasons for giving these talks, that I want to show you how the thinking that I use can be embedded within the water wave problem and makes use of ideas that underpin the Gerstner exact solution. Okay, well, this paper, as you see the date, 1802, appeared in an absolutely obscure Bohemian journal. As far as we know, nobody could have read it. I do not know the history behind it, but I do know that it was reprinted in 1809. It was reprinted in 1809 in Annalen der Physik. And it was there that it became a little more widely read, even though it wasn't taken up. It wasn't really taken up seriously until Rankine wrote a paper which essentially reproduced this, but was based on what Gerstner did. So Rankine in 1868, I think. And that's where at least it came to prominence. 1868. And at least thereafter it was known, but it wasn't really taken very seriously. Now what I'm going to try and do here is, again, as I did with the previous one, but perhaps rather more detail this time, I'm going to try and outline the development of Gerstner's solution. So let's have a look. 63. Couldn't read my own writing. 3s and 8s, when I scribble them, even in my own notes, look a little. So, 1863. Okay, so, well, I've already said this already. It's the only known non-trivial solution to the water wave problem for gravity waves, of course. We are not dealing with ripples. So we're looking at a two-dimensional, steadily propagating wave in infinite depth of water. So it's two-dimensional. So we've got x and we've got z. It would turn out that the flow, this is the weird thing about it, has a non-zero and prescribed vorticity to be associated with the flow. Okay, this is where we need to use the Lagrangian description I mentioned yesterday. It is the one occasion only when I will be using it. So we're going to describe the motion of the particles using two parameters, A and B. Right? With the transformation x prime to a point big X primed function of t and the two parameters, we can do the various manipulative routine calculations. So we can work out what d by d little x primed is. Sorry, when I wrote this out, I was just using dimensional variables. It doesn't matter one jot, of course, how you want to write them. I just get into the habit. If I haven't non-dimensionalized, then I must put a prime on. Irrelevant, of course, in what we're doing here. Right, so it's routine calculation to work out what the x primed and little x primed and little z primed derivatives are. The Jacobian is written out at the bottom there, and clearly for a solution to exist we must ensure that that is non-zero, but something quite interesting happens when it just becomes zero, and we can accommodate that as part of the solution at the end. The velocity components are obviously the t prime derivatives of x and z. We can then compute what the mass conservation equation will become under these transformations. So again, this is the notation I've used before. So we've got x and u, z and w. Okay. I've written out a few lines there, something which, if you maybe you'll get these screens, so you can go back and work your way through it, and you'll find in that I actually ought to have this in front of me, because I've given you a little bit more, yes, a little bit more detail in one or two places, but I think it's later on beyond this, in the notes for you to follow up. So if we compute what the mass conservation equation becomes, so we're computing that, using the transformation into Lagrangian form, we find that this eventually becomes this. Okay? The Jacobian, 1 upon the Jacobian, not equal to 0, dj by dt primed. And consequently, we have, because j is non-zero, we merely have this statement. So that quantity there is not a function of t. Okay, so where do we go after that? Well, of course, we've got to compute what happens to the two components of Euler's equation. So we've got the horizontal component and we've got the vertical component, expressed in Lagrangian form. Right, so we've got the acceleration term over there and under the transformation for the derivatives that were on the previous screen, we can work out what happens to the horizontal derivative in pressure, and correspondingly vertically, the vertical derivative of the pressure, and here is the gravity term sitting in the equation. So we get the routine calculation, we get that, which we can then use to determine dp by dA, or dp prime by dA, and dp prime by dB explicitly and very straightforwardly. Okay, so we now wish that the second derivative does indeed exist, the cross derivative here between A and B on P prime, so a consistency condition is required and we impose it, and that gives us the equation at the bottom there. At this stage, there is nothing about water waves here. Other than the equations we're using, we haven't looked for any special solutions whatsoever. So what we've done is to take the equations, transform them, our Euler equations, describing the water wave problem, just the equations, notice we haven't imposed any boundary conditions at this stage, and manipulate it. It's at this point that we now make a choice. And it is this choice which will give us a particular solution relevant to surface waves in water. So, in fact, that's what I've just been saying, isn't it? So what Gerstner did, having done that development, he then looked for a special solution. He looked for a solution so that the position of every particle at time t is described by a circular path using the labels A and B. So he then looked for a solution which takes the form here. Interesting, I said, put a prime on that if you like. X prime and Z prime. We're looking for a solution which is circular in time, but with parameters A and B. And you'll notice an exponential appearing in here. K plays the role of a wave number. It's constant, and we'll take it to be positive. Right? At the moment, we're not absolutely sure what the nature of the B will have to be. The A will certainly sit between minus infinity and infinity, because it more or less plays the role of what happens this way. The B plays the role of what happens this way. And making choices for B naught is critical, as you'll see. So Gerstner looked for a solution of those underlying equations that I gave you a couple of minutes ago of that form. Okay. Oh, yes, obviously. This maps to a wave which sits in minus infinity, infinity, and between this is infinite depth, remember? Minus infinity up to h primed, and of course h prime just to note what the free surface is. We don't know what that is yet. Okay. Now we do. So the free surface is given parametrically by that. So in other words, if you just evaluate at the free surface, that is what you get as the expression for the free surface. In terms of the two parameters, A and B, and the free surface is denoted by the value B is equal to B naught. The surface, that's the pressure condition. The surface kinematic condition in that formulation is automatically satisfied. And have I got it? And then, I've said that around the wrong way. So with that choice of free surface, the kinematic condition is satisfied. We can then impose the surface pressure condition and obtain the pressure in this form. You'll notice immediately that this doesn't involve A and pressure is constant on particles labelled B. Okay? This only depends upon, all of these are constant, and there's the evaluation on B and the choice B naught, which we have yet to make. Okay, so that was just a matter of just saying, well, okay, what does the solution look like? Does it have any interesting properties? Well, first of all, a typical profile will look something like that. That is a sketch based on numerical integration numerical evaluation of the solution that we've got here. It is also the choice I've made for B naught less than 0. If you choose B naught is equal to 0, and that is absolutely the limit. You cannot allow B naught to be any larger. You'll see why in just a moment. Otherwise, the Jacobian is going to go through 0. You then get this very special cusped wave. This particular wave version of the solution has the property that the vorticity is undefined at the tip. Right. I don't know. So, I'm going to pause for a moment, just check. I'm trying to put together all the bits and pieces without doing too much writing. Well, screen showing. So, if you look at the notes, I've added a bit more information here for you. So, for example, I didn't bother to write it out here, but I've given you the velocity components. And there you'll see that you've got the exponential e to the kb. B is negative. B increasing negatively gives you decay and goes to infinity below, and the velocity field then decays. We have the wave speed, and we have which corresponds to the propagation of waves in deep water. It's a very special solution, therefore. The pressure, I've already mentioned that it is constant on points designated by particles labelled with the B. The A doesn't appear at all. What else do I need to say? Oh, the Jacobian I've written down. That is, it turns out to be 1 minus J. Turns out to be 1, with this solution, minus K B. And consequently, you'll see that if you choose B to be, B sits between minus infinity and B naught. If you had B naught equal to 0, this is 0. It happens exactly at the tip. You can't go beyond that if you wish to have a solution. What else have I said? Oh, I've worked out the vorticity for you as well, I see. Oh, that's exciting. So that turns out to be proportional to 1 over e to the minus 2kb minus 1. So the vorticity is proportional to that quantity. So as b goes to minus infinity, you're going down. This tends to 0, so the vorticity decays. It is prescribed. And you'll also see, of course, as I mentioned a few moments ago, if the upper value of b is b naught, and that is 0, you have a singularity in the vorticity, exactly at the point of the cusp. Right, so what I've tried to do, albeit rather briefly, is to indicate how one can tackle this very special, very unique problem, the mathematical curiosity of the Gerstner flow by introducing a Lagrangian formulation. We have obviously got an exact solution. The particle paths are circles, and we have it's rotational necessarily, and the vorticity decays with depth. One other little ingredient to add is that I mentioned Adrian Constantin got involved in this problem. In 2001, he was able to prove that this is a dynamically possible flow, in the sense that the label set AB is a diffeomorphism into the fluid domain below the surface. I think that probably is where and there is a special cusp solution. Right, so what I've tried to do today, albeit in a rather vague and haphazard way, is to give you a little bit more information about basic material that is available within classical water wave theory. So far as I'm concerned, the Gerstner solution plays a role but in the background. Obviously, the solitary wave solution, and particularly the Scheck squared variant of that, will play a rather more important role in what I'm going to say later on in the week. Okay, so let's take our break. Right, thank you. Right, let me try and collect my thoughts. We're going in a completely different direction now. What I have tried to do up to this point, albeit in a rather general and background vague sort of way, is to just give you a feeling for the nature of the various problems that are involved. One in terms of getting the equations, which we've seen from me and from Catherine, and a little bit about their basic properties. In particular, all I want you to take away from the detail that I tried to outline a few minutes ago is that we have a solitary wave, we have a small amplitude solitary wave, which we'll say more about, I guess, tomorrow, and very much in the background is this notion of the Gerstner special solution, the only exact, non-trivial exact solution. I think it was important that you know that such a thing exists. As I've already indicated, it doesn't seem to play much of a role, and I wish that I had taken it more seriously when I was putting together the material for my water waves book. I deliberately thought about it and thought, no, it's of no interest to anybody. It's a complete waste, so let's forget about it. From what I now know, I think that was a mistake. So that's water under the bridge. Let's move on. This is completely different. I'm going to do a bit more talking and a bit more, I hope, a little more precise, because I want to describe to you the way in which we think about constructing ultimately solutions of differential equations using parameter asymptotics. I'm going to assume that your background in this area is 0. It may not be, but I'm going to assume it's 0. Certainly, I would expect that using these techniques is not something you're familiar with. This is absolutely not rigorous at all. It is a formal presentation. It gives you a very important guide as to what is going on, and I'll explain what I mean by that in a moment or two. So I want to introduce you to the basic thinking. You might well have questions and criticisms as we work our way through this, more so than anything else I've done up to now. So we're going to talk about asymptotic expansions with a parameter. There are many general choices I could make. This is meant to be absolutely and no more than a very, very simple-minded introduction in the hope that I can just get over the basic thinking behind what we're doing. So I'm going to stick to real-valued functions, scalar functions. We'll have just one variable, a scalar variable, and a single parameter. Yes, we can certainly have vector-valued functions of vectors, and we can have more than one parameter. Of course, if you do have more than one parameter, you can only cope with one at a time, unless you have some exceptional cases where you wish to relate the parameters, which physically is not likely to be of importance or relevance. So, very simple indeed. Okay, so in order to construct an asymptotic expansion using the parameter epsilon, at the moment, I'm going to make one extra comment. Bear in mind that we're not going to be given functions. We don't start with a function. We'd love to be able to start with the function, but the function would be the solution of the differential equation, and that's usually what we're trying to find. So a lot of the thinking that I'm going to give you just for the moment is not directly relevant, because we cannot start from this position. So in order to construct an asymptotic expansion with respect to a parameter of a given function, we need to be given or choose a suitable asymptotic sequence. I've labeled it the set of functions phi sub n, n running 0, 1, 2, etc. This sequence is defined so that each term is smaller than the preceding one in the limit epsilon tending to 0. So phi n plus 1 over phi n, functions of epsilon, tends to 0 for every n, 0, 1, 2. That defines our asymptotic sequence. What asymptotic or which asymptotic sequence you use for a given problem is, I think the phrase I might use is up for grabs. It's most certainly not unique. Okay. The usual notation that we will use, this is using little o and big O notation, is that phi n plus 1 is little o, and that is meant to be a little o, the big O's be rather larger than that, little o of phi n as epsilon tends to 0. Or one other comment, I will always assume in this system, I probably haven't written it here and I should have done, I will always take epsilon to be a positive parameter, so we're going through to 0 through the positive numbers. Right, so this is our asymptotic sequence. That is going to be the basis upon which we represent construct a representation of that function. Okay. Indeed, I will write such a representation. So it's just a matter of, if you like, expanding the function in terms of this sequence, based on this asymptotic sequence phi n, and determining what the coefficients are, as, of course, in this construct, functions of x. I've also now used the big O notation to indicate the error measured in terms of epsilon. So what x is doing in here is, of course, absolutely critical. We'll get to that in just a moment. Okay. There are two ways of writing it. The one which indicates, and sometimes this is necessary because the error, you may need to be quite explicit about the nature of the error, and implicitly it is there, but sometimes, maybe I might say quite often, you will find that what's written is the varies as or behaves as, is the way I would say it, symbol, which is this one, which just gives the terms that you've retained or you're interested in without stating what the error actually is. So this is a slightly looser way of writing the same piece of information. Okay. I've already made this comment. The asymptotic sequences that we use are most certainly not unique. Sorry, I haven't got to that point yet. The asymptotic sequence has got to be suitable for the particular function you're interested in. Certainly, it would not be unique here. I'll come to that in a moment. More importantly, depending upon the function, you will choose an appropriate asymptotic sequence. It is clear that a sequence like that has no relation whatsoever to a function like that for some x not equal to 0. Okay. Here it is. It comes up here. Asymptotic sequences are not unique. Normally, we're in a position of assuming them, or possibly being given them, or we have a very strong guidance from the underlying differential equation as to what the asymptotic sequence should be. But it's not unique. The normal procedure is if you wanted something which behaves something like this, even though you could use any one of these and any other number you can think of, we would normally just simply use the simplest one, naturally. But you need to bear in mind that the asymptotic sequence that you elect to use, and there will be occasions when, because of the algebraic complexity or the way in which a particular parameter appears in a system, that you might indeed opt for one of these rather than that. But they're equivalent. Clearly, because the behavior of these functions is the same as that, as epsilon tends to 0. Okay. Now we need to start thinking about what's happening to the x. Let's suppose that we are given a function and it is defined in some domain. And we then, for any fixed x, construct an asymptotic expansion. So I'm given a function and it's for x in some domain. I then choose, be given, whatever, a particular asymptotic sequence. We then construct the asymptotic expansion on that basis for x within the domain, any general x within the domain. The construction is, of course, what's the word? I just say algebraically. Is algebraically constructed using the expansion based on epsilon via the asymptotic sequence with coefficients which depend upon x. We construct the asymptotic expansion, and in principle, it has to be for every n greater than or equal to 0. Okay. So the question we now ask is the asymptotic representation valid for all x's in the domain? That is the crucial question we have to ask in this way of thinking about the construction of the solution. If it turns out, and this is the best, of course, of all possible worlds, if it turns out that for every x in that domain, notice here I'm now not just looking at the asymptotic sequence here, it is the term in the expansion involving the x. So if a term in the expansion involving the x and the epsilon is always, and for every n, smaller than the next term, as epsilon tends to 0, we have what we will call is a uniformly valid expansion. You'll see here, I'll say a little bit more about it in a few minutes. We're not saying anything about convergence here. We're talking about, well, the phrase I'd like to use is that ultimately in a differential equation, and I'll just think of there being one parameter, you've carried out a non-dimensionalization, you've scaled, maybe whatever, you've got an equation or a system of equations with a parameter. The parameter will label various terms. One or maybe more terms. And if you were then using, if we just had epsilon, you would be tempted to say, okay, let's use epsilon to the power n as the asymptotic sequence. That will label and extract various terms at various orders. In a sense, you can use the parameter to identify and extract, if you like, physical properties of whatever it is you're looking at. In a sense, that's the way to think about what's going on here. It may be small, a weakly nonlinear problem, in which case you would find that you would have a linear problem initially, the leading order, and then you would have an extraction of terms that give a measure of what's happening at the next order via the nonlinearity. Of course, the question then becomes, does it remain weakly nonlinear or not? That's part of this idea. So, I'm giving you what I will regard as the definition of a uniformly valid expansion. It's one that satisfies this condition for every n. Oh, one other comment to make, apart from having a drink. I'm couching this in terms of perfection. That is, for every n. Now, let's be realistic. If you're dealing with a complicated system of differential equations, the chances are you're not going to be able to get more than the first few terms. Quite often, though, you might well be able to identify where there might be singularities and be able to just look at the neighborhood of the singularities and just see what happens as x goes to some particular x naught down the line, down the asymptotic expansion, and then see if there is indeed a non-uniformity. You don't have the full detail. You don't have all the information about this coefficient an of x, but you may have sufficient from the differential equation. Obviously, if you're given the function, then it's really trivial. From the differential equation that tells you whether you do have a singularity or not. If you do have singularities, the chances are this is going to break down, and you have to rethink the whole system. Okay, so we've got an expansion. So in this terminology, we have a function, an asymptotic sequence, and it's quite easy to find, to check whether the asymptotic sequence you've chosen is actually consistent with the function. In other words, can you actually define this system and the coefficients? Okay, I thought perhaps, I know it's going to be rather simple-minded, but it might help to fix thoughts, particularly if this sort of thinking is very unfamiliar to you. So let me look at a really simple example. I think I've got two here, actually. One slightly less simple. So here's a really trivial one. Okay, here, epsilon is always taken to be a positive parameter, and we're interested in epsilon tending to 0. You'll notice that this is an unbelievably well-behaved function in that domain. Absolutely trivial. Indeed, all you need to do is to use a binomial expansion, and you can go to as higher order as you wish. Every single term in this expansion is completely defined, and there are no non-uniformities. In other words, each term in here, as a function of x in that domain, remains, doesn't involve any singularities. In other words, if you balance these terms up, there is no breakdown. Oh, sorry, I've jumped ahead. It works. So this representation, and to as higher order as you wish, trivial calculation, is uniformly valid on the domain. And it is important that you appreciate that, simple-minded though it may be, that you must be very clear about the domain in which you are representing the asymptotic representation of the function. Okay. Now, this example is not quite so straightforward, as you can see. So this time I've taken the epsilon is a positive parameter. We're interested in constructing a solution epsilon going to 0. Oh, yes, you'll see what happened here, and the same is going to happen here. When you are given something as simple as a function, and certainly a simpler function as this, then the asymptotic sequence is, in a sense, automatically generated. You don't have to choose it. When you're dealing with a differential equation, you have to choose. make a choice. You may get it wrong and you have to start again. Here, of course, you just use an elementary mathematical technique to represent the function. And if you like, after the event, having done it, you say, oh, of course, the asymptotic sequence is epsilon to the n. Now, this is what life is very, very simple in this neck of the woods if you're given the function, not if we're not, if we have to start with a differential equation. Okay, so let's use this thinking that I applied up here to this problem. So I fix any, not choosing a special x, any x. So I'm avoiding x is 0. But any other x you like, just fix it and do a binomial expansion. Straightforward. And again, for this problem, making sure that we're avoiding x is 0. You can see the problem here. Avoiding x is 0 for any other x, just do the expansion. Use the binomial expansion. You can get as many terms as you like. And we're again using the asymptotic sequence. We find it's the natural one because that's what comes up when we just do the elementary expansion, is epsilon to the n. This yes, sure. No, I don't think so. Let's just have a look. No, I've taken that. Oh, have I got that? That comes out as a factor, right? So that's epsilon. But no, it's. If I take that out, you're happy with the first term, okay? That leaves me with 1 plus epsilon over 1 plus x. The binomial of that gives me 1 plus a half epsilon over 1 plus x multiplied by. Yeah. Yes. So I chose to take it in rather than leave it out. You okay? Thank you. I don't think it makes too much difference to the asymptotic expansion, fortunately. Happy worried there for a moment. Right, now this problem, okay, this one down here. Now, bear in mind that very simple-minded idea I had about the notion of a breakdown. Now, as the domain is x greater than or equal to 0, as x increases, so in fact this term actually gets smaller. If you like, it gets better. Okay, it's a better approximation as x increases. However, you've all seen it, we're in deep trouble if I let x tend to 0, and x equal to 0 is in the domain. As x tends to 0, this term gets, for any given fixed epsilon, think of it like that. As x tends to 0, this gets smaller, this gets bigger, self-evidently. There is an x, a size of x, which balances these two terms. At that point, we say that the asymptotic expansion has broken down. By that I mean that this representation of that function is no longer valid. We must not use it. Okay, so here we are. I've just written it down here. So we say the asymptotic expansion breaks down. Sorry, yeah, okay, I know what I'm going to do. So the asymptotic expansion breaks down for any x's in the domain for which succeeding terms in the asymptotic expansion become the same size. And that can happen anywhere down the asymptotic expansion. It can be rather tricky and interesting if you've got terms which are exponentially small at the far end, which are preceded by algebraically small terms. So I'm going to use, in this introduction to these ideas, and I said at the beginning, maybe even with a small apology, I'm assuming this sort of thinking is rather foreign to you. I'm going to be really simple-minded about it. So we've got if there is any pairing of terms, that is for any n, we get succeeding terms the same size. So it needn't happen first and second. It can happen fifth or sixth or whatever. If it happens anywhere down the line, your asymptotic representation, which is ordering the terms in terms of epsilon, has failed. So, okay. If I go back again, I'm sure you've seen it. I've already indicated it, but let's just go back. If you now look at this, you will see that as x tends to 0, you will have, roughly speaking, square root x, the same size as epsilon over square root x, which gives you x is order epsilon. If x is of size order epsilon, then these two terms become the same size. What the size actually is irrelevant. They've become the same size. You can no longer order this one as smaller than that one for these x's as epsilon tends to 0. Okay, so Right. So the little example shows that we have, in this terminology, a breakdown of the asymptotic expansion for x of order epsilon. And what you're now seeing is that we have a nomenclature which would say, and I haven't written it on the board, but I'm going to say it to you now, the previous expansion before breakdown, we would say that that was valid for x's order 1. Now, by order 1, I mean that it is independent of epsilon. Okay, it can be as big and small as you like, but not measured by epsilon. Okay, it's order 1. Here we have a breakdown, when x is order epsilon, telling us that we have to carry out a rescaling. Okay, so we now operate with a scaled x, which means that if I now, I'm going to use the same terminology, think of big X as being order 1, so it's anything you care to choose independent of epsilon as epsilon tends to 0, then we have little x measured, in this case, proportional to epsilon. Of course, all that's going to happen here is that we have the same function. It just looks slightly different. There's nothing, the function has not changed. Of course not. All I've done is just to redefine the variable. And ultimately, all I've done is to change the variable little x by a constant times another x. Trivial. However, when you interpret it in terms of epsilon, and epsilon going to 0, we have got a different structure to the function. We had a structure, epsilon going to 0, little x is order 1. We now have a different structure. Big X is order 1. By order 1, again, I mean fixed as epsilon tends to 0. And then we get that behavior. So this time, you will see that the size of the function, which I've now relabeled big F, having defined it in terms of the new variable big X, is proportional to root epsilon. What you'll now observe is that this is defined on big X is 0. That is defined on big X is 0. In other words, my new asymptotic expansion, which is a different function, but trivial all the same, it's a different function, does enable us to evaluate on big X. If big X is 0, that clearly corresponds to little x is 0. We've got to the origin in this particular domain, and that's perfectly well defined. And indeed, if you like, we can also say that in the neighbourhood of x is 0, here's the leading order, and we know what the correction term is. All perfectly well defined. Is everybody comfortable? Yes? Straightforward? I hope. Okay. Oh, yes. Oh, this gets exciting now. Well, I'm sorry. I'm simple-minded about these things. Right. So, yes, let's go back for a moment. So sorry, my mistake. It's the next bit. That's what I thought I'd written up. Okay. So, I've already explained the first line there, what I was saying, but now, this is where it was getting exciting. If you go back to the expansion, I'll uncover it again in just a second, that is not uniformly valid. As big X goes to infinity, as you move out of this narrow region where little x is order epsilon. So let me flip back. Okay, right, now have a look at this. And now let big X increase. So you're moving out of this order epsilon neighborhood of the origin. You move out, and of course, you can see we have a breakdown, because this increases like square root x, this increases like, or x to the 3/2 times epsilon. This term dominates and eventually, well, can dominate, and eventually, from our point of view, these two become the same size. But they become the same size using the scaling that we just come from. So we go back to where we came from. If we were given, we could be given this function and the same domain, and then work from the origin outwards. Here we've gone from order 1 inwards. Okay, everybody happy with that? Okay, so one other thing. Again, I don't know whether this is something which you're comfortable with or not. At least for most problems, even with exponentially small terms, you have to adjust very slightly the way in which you interpret what is known as the matching principle. I want to show you that, in fact, when you've got an expansion in, let's call it an outer region, an expansion in an inner region, for this problem there are only just 2 regions, there could be many more, 2 regions, and And we've now shown that this one breaks down to give you this one. And indeed, we found that this one breaks down to give you this one. There is an intimate relation between the two of them. And it's very close. It's very close, algebraically speaking. So, the two expansions then that we've got are said to match and to satisfy the matching principle. Right, so put loosely, again, I can put lots of m's and n's. Indeed, much of this has been couched in terms of an expansion operator. You apply an operator to the function, which gives you this expansion, an operator on the function, which gives you that expansion. Then you apply that operator on that and that operator on that. All of that can be couched in rather more formal terms than I'm doing here. But the idea, that's all I want to show you. I want to show you what the idea is amazingly, well, I think it's amazing, and it's amazingly simple. So, expressed in this very simple terms, so we take the first expansion, which you remember was written in terms of the original, the order 1 variable, little x, okay? You write it in terms of the second variable, which, I mean, up to a point you think it's a reasonable thing to do, and you expand it. Now, when you expand it, no. I won't let the cat out of the bag yet. Just pause for a moment. You expand it. What you do there is not easy. I mean, it's not. You have to think about what you mean by expand. And you expand it. What you'll find is that it agrees precisely. I'll explain what I mean in a moment. By doing it the other way around. So you start with the expansion. For us, it's the inner region using the big X variable, and express it in terms of the little x variable and expand that. So. As you see, I've written up on the screen. We're going to check it. Okay, so I'll have to flip backwards and forwards here to make sure. So we consider the expansion of f of x, or maybe I won't have to actually. So here, ignore this for a moment. So here we have what I wrote down before. The first two, this is where it gets, we have to be precise. The first two terms in the asymptotic expansion, and we could have had more if you want them, no problem at all, we can have as many as you like. The first two terms I have elected to write down because I don't want to worry about higher order terms. That's a good enough approximation for me, maybe, whatever. I then express that in terms of the new variable. So by writing it in terms of big X, if you like, we're right on the edge of validity. Okay? Think of it like that. We're right on the edge of validity. This, of course, now depends upon big X and epsilon. And in the terminology that I just used, I said expand. Okay? Right. Now, I have expanded it using the asymptotic sequences. Asymptotic sequences, because one involves epsilon, the other one root epsilon, that underpin the problem. And I get that by using the binomial expansion. So I then go ahead and I just expand this in the absolutely traditional way. However, I remember something. I remember that when I did the expansion that gave rise to the solution, the asymptotic representation using big X, the only information I extracted, maybe that's all I was interested in, was root epsilon and epsilon times root epsilon. Nothing else. I haven't got any more information about the higher order terms. I never found them. I could find them, but I didn't find them. So the expansion here has got to be an expansion consistent with the other, sorry about this, with the other expansion. Okay? So you write it in terms of a big X, expand, but when written in terms of big X, these are the only two terms that we have, root epsilon and epsilon root epsilon. So we have now got an asymptotic representation of an asymptotic representation. This one written in terms of little x, expanded in terms of the other variable that we've chosen to use in this scenario. Okay, now we do it the other way around. So the problem posed in the inner region was expressed by big F of big X. So we do exactly the same thing. So this function here, by the way, notice that this is not exactly this. You might have thought it was going to be, but it's not. So this is the first two terms of the expansion that we constructed, binomial expansion using the big X variable. Write this, so we're now on the, if you like, the outer edge of the validity of this one. We now write this in terms of the little x variable, and it gets a little more exciting. You see, obviously, because of the relationship between big X and little x, we've got little x over epsilon. Expand that, keeping, well, I didn't use the phrase, but it's obvious, isn't it? You do this expansion keeping big X fixed, epsilon going to 0. You do this expansion, following the same rules, binomial in this case, may have to be more sophisticated if it's a more complicated function, keeping little x fixed, epsilon tending to 0, and you will find that retaining order 1, remember what we had up here? The only information we have from the outer expansion is order 1 and order epsilon. We have no other information. So there's no point in going any further. I know nothing about epsilon squared, epsilon cubed. Do more work, I can get them, but I haven't done. So I must stop at that point. And you'll see that when you do this expansion, you get these terms scattered all over the place. Okay? However, I leave you to just check that if you take this expression and this expression and choose to write them in either big X or little x, I don't care which one you choose, okay? They are identical. Those two functions are identical when expressed in terms of the same variable. So we've got, if you like, a beautifully smooth transition from the outer expansion to the inner expansion. We have a way of talking about the validity in the sense that this one is valid for little x's order 1, this one is valid for little x's order epsilon, which we've called big X, and we have a smooth transition one to the other. Now, this is the sort of language and technique that I was brought up to use, trying to tackle applied mathematical problems. Okay, I'm now going to make a few more general comments. I'm not actually sure what I wrote here. Oh yeah, well, I've already started to talk about this. So all that I've shown you, it looks beautiful, and it is simple when you're given a function. Our big problem is that we are going to be given a differential equation, probably a system of differential equations. Probably, I'm only going to think of using one parameter, a parameter scattered all over the place. But because we've non-dimensionalized, we've introduced suitable maybe order 1 parameters and a small parameter that's going to be the guiding parameter to tell us what the structure of the problem is. We have a system which does not give us any further information other than that which is in the equation. And so the first sticking point is, what asymptotic sequence do you use? And sometimes it is not obvious. The bottom line is, you just have to try. What you're looking for is a sequence of problems one hopes that one can solve, but at least a sequence of problems which enable you at every order, in principle anyway, to get every term and to be able to examine, again, this is the best of all possible worlds, any singularities that appear that would then lead to breakdowns. So our expansions are to be solutions of differential equations with parameters, and the bottom line is you have to just try. Usually the equation gives you a very, very good guide. Actually, if you add to that the fact that in applied mathematics, in many of the problems I'm sure you're interested in, you do have some physical principles there, then you know the sort of balance you would be looking for, and that might guide you. You want this at this order, this at that order, and the only way that will happen is if you use this asymptotic sequence rather than that asymptotic sequence. So maybe a little bit of the physics would help guide the choices that you make. Right, obviously it's not something I've touched on at all. When you're doing asymptotics, one hopes that in the background that you do have some existence, certainly, and hopefully uniqueness of the solution that you're trying to seek. There's a lot you lose, you see, when you're using asymptotic expansions. You just lose a lot of information because you're throwing stuff away at each order. So the normal procedure is to, if we have a theorem that gives us existence and uniqueness, we're in a very strong position. Very often, though, the problems we're dealing with are very complicated. We do not have those sort of underlying theorems. The best we can hope for is that as we solve the sequence of problems, see that each one of those has a clear, in isolation, existence. That is, we can definitely find the solution, and we can put it in the context of the overall problem. But it's done piecemeal. The first term, the second term, third term, and so on. Okay, it's obvious from everything I've said in my whole presentation, this is purely formal. the existence in terms of the class of functions that we might be interested in is going to be given solely by what happens at each order. We have no global statements that we can possibly make. Right, and obviously that notion collapses if we have a breakdown, but we know how to handle a breakdown in terms of rescaling variables. Obviously, I have not touched on this at all. I'll be blunt. It does not normally play a role in classical asymptotics of the sort that I'm interested in. What we're trying to do is to extract elements of the equations, elements that describe particular types of phenomena in the flow process. It does happen sometimes. I've indicated here that it does happen rarely, but normally that is not the situation, and we're not using it. We're not using it for that purpose. We're using it as a labeling and extraction purpose to try and get sequentially a sequence of problems. We're not asking the question, if I went to infinity, what's the convergence of this process? We're looking at, if you like, the physical properties that are generated using this approach. Okay, well, obviously you're very familiar with convergent expansions. If you are working with asymptotic expansions and you want to ask these sort of questions, then the best you can do is to use the standard procedures for divergent expansions, which just says that given an x, in this context, I'll use the notation I've used so far, given an x and given an epsilon, I will assume you can find sufficient terms that you require. There will be a particular number of terms which will minimize the error, but that is the best you can do. If you're getting, I was rather intrigued to learn many years ago that G.H. Hardy wrote a fantastic book on divergent series. Maybe it's not what you expected him to write about, but it's a big thing. And his view was, it's in the book there, that you get more information out of divergent series than you do out of convergent series. Being convergent is convergent, end of story. But if it's divergent, there are lots of funny little things going on in there, and maybe you're going to get more information out. So, yeah, that's the best I can do. It's very rare in practical problems of the complicated nature that we encounter in water wave problems that you're going to get a convergent expansion. If you're really worried about the sizes of terms, you can do something. But what I want to emphasize is that that is not the purpose of the exercise. The purpose of the exercise is to identify terms stroke properties in a flow field. Okay. Oh yes, I thought I'd just mention what typically happens in general wave propagation problems, that we do get some very strong guide. We get the structure of the solution, so we know the nature of the solution, and we usually get a very strong guide as to regions of validity, and quite often we can prove theorems that will indicate that, yes, our solution, asymptotic solution, is valid on a restricted time domain. Now, you can't let time go to infinity, but you can do it on a restricted time domain, and maybe we can get some numbers to be precise about that, given suitable initial data. I'll say a little bit more about that, I guess 3A, which is when I'll be doing, or touching on, Korteweg-de Vries equation. Oh yes, well, I've put it in the notes, so if you're interested, try and do it without looking at the notes, but the note, I've given you the answer. So here is just a little something to leave you with using these very simple ideas. Here, I have gone out of my way to include the sort of behaviors that are a little bit beyond the truly trivial. So I've got an exponentially small term in here. So obviously, if x is positive, this is exponentially small, but you can clearly see because I've chosen the domain to include x is 0, this immediately becomes 1. So you've got very exciting things happening for x order 1 in my terminology, and naturally x is order epsilon. And to make it even more exciting, not only have I got x upon epsilon, I've got epsilon times x. And that might indicate to you that you've got 3 regions to worry about. Not 1, not 2, but 3. So if you want to have a little game with yourselves, have a go at that in your free time, and you can check the answer. I think, well, I've done that already. We finished.